We'll be looking at the June 2023 paper. We're looking at question 20. In this question, you've got the Kw, which is the ionic product of water, and there's two different values given of it at different temperatures. It's asking to calculate the pH of water at 40 degrees Celsius. So at 40 degrees Celsius, now you see the expression of Kw is as follows. Kw is equal to the concentration of H plus ions multiplied by the concentration of the OH minus ions. Now, in this expression, Kw is a higher value, and because this is of water, we can assume that the concentration of H plus is equal to the concentration of the OH minus ions as a 1-to-1 ratio, because you see pure water will dissociate into H plus ions and OH minus ions, and these two dissociate in a 1-to-1 ratio to each other. So what that leaves us with, we can substitute OH with H plus, so this gives us H plus squared. And so if we work out the concentration of H plus, it's 2.92 times 10 to the minus 14, and we square root that, that gives us 1.7088 times 10 to the minus 7, and then we take minus log to the base 10. So whenever we're doing any kind of pH calculation, we always use the expression minus log to the base 10 of the H plus concentration. Minus log to the base 10 of the answer. That gives us to 2 decimal places 677. This tells us that water at a higher temperature is slightly more acidic because pH 7 is neutral. In the next question, it's asking us, table 20.1 shows Kw values at 25 degrees Celsius and 40 degrees Celsius. A student suggests that water is neutral at these temperatures. So it doesn't matter what the temperature, that water is neutral. And going back to the equation, neutral as in the charge, not the pH. We've spoken about the pH in part 1. Here it's about, you can think of it as charges, and you see that the concentration of H plus is always equal to the concentration of OH minus ions. That's why water is still neutral. You can refer to the moles of water, the moles of H plus ions and OH minus ions being the same also. The next question, a student reacts strontium metal with water to make this concentration, this volume solution. The solution contains this mass of strontium hydroxide. Write an equation for the reaction of strontium with water. So in the equation, we've got strontium reacting with water to give us strontium hydroxide. Hydrogen gas is also given off, and we can balance it accordingly. It's then asking us, calculate the pH of this solution of strontium hydroxide at 40 degrees Celsius. So we're going to be using a different Kw value, which is this one over here, 2.92. And we've got our strontium hydroxide mass. So what we do, we work out strontium hydroxide, strontium. Now we've got 0.145. Let's do mass over the MR of strontium hydroxide. Strontium is 87.6. So 1 to 1.6. This gives us 0.00111924 moles. Now we want to work out the concentration. And an interesting thing here, this is the moles of strontium hydroxide. You see for every 1 mole of strontium hydroxide, there is 2 moles of hydroxide ions. So we need to times this answer by 2. So this answer, we multiply by 2. That gives us the concentration of the hydroxide ions. And then we do N over V is equal to C. We want to work out the concentration of hydroxide ions. And we so divide that by the volume. The volume is 250 centimeters cubed, which is 0.250 decimeters cubed. So multiplied by 2, this answer. And divided by 0.250, this gives us the concentration of hydroxide ions. Notice I'm not rounding up. We round up at the end answer. And so Kw in this case is 2.92. 2.92 times 10 to the minus 14 is equal to the concentration of the hydroxide ions multiplied by the concentration of the H plus ions. We're going to plug in this value. This value goes in here. And so the concentration of the H plus ions is equal to and then plug it into the pH expression, minus log to the base 10 of this concentration. (11.51). Wants our answer to 2 decimal places, 11.51. Yep, and the mark scheme supports that. 5 marks, step by step. With hydroxides, where you've got 2 moles of hydroxide per 1 mole of the compound, please be mindful of that. Next question. A student reacts 1 gram of strontium carbonate with excess dilute nitric acid. A gas is produced. Construct an equation for this. You see strontium carbonate, you learned this in GCSE, a carbonate plus an acid goes on to give you the salt, water, and carbon dioxide. We then balance, put a big 2 there, and I believe that is balanced. Yes, it is. Now, in this question, the student originally reacts 1 gram of strontium carbonate. In part 2, the student then reacts 1 gram of calcium carbonate. Explain why the student's 2 reactions produce different volumes of gas. You see, you can explain this in words, you can explain it with calculations. We'll do both. You see, with strontium carbonate, if you've got 1 gram, the molar mass of strontium carbonate, we just quickly work this out, 87.6 plus 12 plus 48, 147.6, and calcium carbonate, 1.00 divided by 40.1. You can see this would work out, give you the moles of the carbonate, and also it's a 1-to-1 ratio with the amount of carbon dioxide produced. So you can see that strontium carbonate, because it's got a greater molar mass, it would produce a smaller amount of moles compared to calcium carbonate, which would give you a greater number of moles. And just putting that into words, so this will be greater moles of the solid, which in turn will give you a greater volume of CO2. Putting that all into words. Refer to the molar mass, refer to the MR to get those 2 marks. Moving on, a student reacts magnesium with this volume and this concentration, hydrochloric acid. The student also reacts excess magnesium, so both are excess, of magnesium with same volume, same concentration of ethanoic acid. Construct an ionic equation for the reaction of magnesium with an acid. Ionic equation, we do not use the spectator ions. So you've got magnesium, the metal, will react with the acid, and it's the H plus part of the acid which we're concerned about. This goes on to give you the magnesium turns into a 2 plus ion because it's in group 2, and the H plus ions gain those lost electrons from magnesium to give you hydrogen gas. And we then just balance it accordingly. This is your ionic equation. It's asking why do these two reactions of magnesium produce the same volume of gas but at different rates? These two reactions, HCl, in a solution, it completely dissociates, so it is a strong acid. And the ethanoic acid, which is the key ingredient in vinegar, is a weak acid. Now, you see, it's asking us to refer to the rates. There's going to be a greater concentration of H plus ions. And so that's going to result in, if you remember from last year, year one, that will result in more frequent collisions, which explains why the rate is greater with HCl. Now, referring to the last, it still produces the same volume of gas. Why is that? Because you can word it differently. Both acids still eventually they have the same number you see with the weak acid. This is just an extra to explain. As the weak acid, so as the concentration of the H plus ions gets used up, so this goes down, the equilibrium starts shifting more and more to the right-hand side until all of the ethanoic acid is used up. And it ends up giving the same amount in moles of the H plus ions. And that in turn will give you the same volume of the gas that is produced. So these are your 3 marks. Moving on. Butanoic acid is a monobasic acid. And this term, monobasic, I've heard monoprotic. Let's just double check this definition. Monobasic. What is meant by the term monobasic? Anyway, it's an acid and it gives off 1 H plus, mono. Mono is 1. And this supports, so this idea that one molecule of butanoic acid gives 1 ion of H plus. Gives or forms 1 ion of H plus. That's what it means by monobasic. Now this next question is a buffers question, and it's worth 4 marks. It's a big calculation here. Now, what is a buffer solution? A buffer solution is where it maintains its pH on the addition of a small amount of an alkali or an acid. So it maintains the pH of that solution. Now, you've got this. Oh, they want you to work out the Ka. So you see, you've got butanoic acid, CH3. I'm just going to write down the expression. Now, you see the Ka expression for the buffer solution is going to be the following: CH3, CH2, CH2, COO minus, and H plus. You see, when you're dealing with a buffer solution, the top part of the expression is not equal to H plus squared. No, no, no. The concentration of the ion is the concentration of the salt that's used to make the buffer solution. So how much? Okay. So we are going to okay. So we've got the mass of potassium hydroxide. Let's work out the moles. 3.39 divided by KOH. Potassium is 39.1 plus 17 is 56.1. Zero point zero. Now, we're dissolving that. Actually, we're going to react that with the butanoic acid. The butanoic acid, we've got 0.376. That's the concentration. Let's multiply that by the volume. Volume times concentration gives you moles. That gives you 0.094 moles. Ladies and gentlemen, you see when you react these two together, this is all going to get used up. So this will get all used up. Oh, sorry, not the acid. The potassium hydroxide will get used up. And so you'll still have some excess butanoic acid and the salt of the butanoic acid. You'll have potassium butanoate. And the amount of moles of that will be the same as the KOH that you started off with. So you'd get this much moles of potassium butanoate. This is the salt. So now that you've got, that's the amount of moles of the salt, how much of the butanoic acid will we have left? You would have 0.033572 moles. And now we work out the concentrations of both. The total volume is 250. So let's just call it the salt concentration is equal to 0.0604278 over 0.250. The volume in decimals cubed. Gives you 0.2417112 moles per decimeter cubed. And for the butanoic acid, concentration, that will be so now we've got this concentration will be here. This concentration is of the weak acid. And for the H+, the H+ concentration is going to be 10 to the power of minus pH is equal to the H+ concentration. And they've given you the pH in this question is 5.07. So this here will be 10 to the power of minus 5.07. That goes in here. So we just plug in those values, and that will give us the Ka value. And we'll give our answer to 3 sig figs, 1.53 times 10 to the minus 5. Yep, just the answer itself would give us all 4 marks. If the answer is wrong, then the examiners will start looking at your working out to see if you've gained some marks out of the 4. But the mark scheme supports that. Moving on. It's asking a buffer solution, and it's referring to its definition here. A buffer solution has pH 4.50 when a small volume of water is added to this buffer solution. The pH does not change. And here we need to look at the expression. You've got the Ka value, which remains constant. And you see the conjugate base ion, A-, and the concentration of the weak acid, they both get diluted by the same amount. They both get diluted by the same amount when you add water. And so this, because they get diluted by the same amount, their concentrations are the same, and therefore the concentration of the H+ will also be the same. So the pH does not change. And how do we put that into words? Yeah, all they want you to say is ratio or proportion is the same. Different ways to word this. Something along the lines of change in the weak acid concentration and the conjugate base is proportional. Yep, that brings us to the end of question 20. See you next time.